this is Miss Ward. Tonight your notes are going to be on our last unit, our last concept in this unit, Concept 5, and we will be applying Newton's laws. So at this point we've discussed all three of Newton's laws and how they relate to one another, and now we're going to talk about how you can apply them. So first of all, something that's super important and we've been doing in class by this point many times over is using free body diagrams. These sketches help us show all of the forces. When you do a sketch that shows all the forces acting on an object, it's referred to as a free body diagram, and as you should well know by now, this is how we calculate the net force of an object. Weight is a gravitational force, and it's measured in newtons. Mass is a measure of the inertia of an object measured in kilograms. This is why you weigh less on the moon and there is less gravity, but you still have the same amount of mass. Your inertia doesn't change, just your weight. Weight and apparent weight are different things, though. So apparent weight is the way you experience weight from the force exerted upward on your feet from the floor. So your apparent weight is essentially your normal force that you feel. So gravitational force is always pushing down on you the exact same. The gravitational force never changes. But sometimes your normal force can change. And so that force that you feel, the normal force you feel, actually is what makes you feel your weight. If the floor exerts more force on you than your weight, you feel heavy, and if the floor exerts less force on your weight than your weight, you feel light. So if you were to calculate your weight using your apparent weight, you would use this equation that we're going to get to. So imagine that you're in an elevator and there's two forces on you. Your gravity, which is always constant pushing down, and the upward force, the normal force pushing on you from the elevator. All right? In a normal circumstance, your apparent weight minus your weight is equal to your mass times the acceleration in the y direction. Well, the acceleration of an elevator, it's just the acceleration of the elevator is in the y direction, so therefore your acceleration equals the acceleration in the y direction. So it's just your apparent weight minus your weight equals your mass times your acceleration. Alright, and so if we take that and we move them on over, so on the last slide I wrote, hold on. On your last slide, I said that your apparent weight minus your weight equals your mass times acceleration. So what we've done here is we've added weight to both sides, and that has given us this equation, where your apparent weight is equal to your weight plus mass times acceleration. Well, as we said before, your weight is really just that force of gravity that you feel, so we can substitute that with your mass times gravity, of the acceleration due to gravity. So we have your apparent weight equals your mass times the gravitational acceleration plus your mass times acceleration. Alright? And so in a normal circumstance where nothing's moving up and down, this acceleration is 0. So on a normal day when you're just standing around, this is 0, so it cancels out. So your apparent weight is equal to your mass times acceleration due to gravity, which is just your apparent weight would equal your weight when this is 0. But that's not always 0. So in circumstances where you have an acceleration, your apparent weight will be different. So what does this mean? Well, if your acceleration is less than 0, then that means that the elevator is going down, and so therefore you're going to feel lighter. Essentially, if you look back on this last slide, alright, if this acceleration is less than 0, so it's a negative number, then that means that this whole piece